the Study Guide podcast for Chapter 45.48. Okay, starting off, this is Lesson 4.7. We are evaluating trig functions. So remember, when we are evaluating inverse sine of 1, really what we're doing is we are looking for the sine of what angle theta, if we want to call it theta, the sine of what angle theta equals 1. And remember, if we're thinking along our unit circle, if we're thinking with our unit circle, we have to restrict the domain. So, or the range, moreover, is we know we have to grab our angles from the first or fourth quadrant if we're doing inverse tangent or inverse sine. And we also have to rename these. Instead of 11 pi over 6, we call it negative pi over 6. Instead of 7 pi over 4, we call it negative pi over 4. Instead of 5 pi over 3, negative pi over 3. Don't use our degrees. So inverse sine, inverse tan, we go with those two quadrants. And for inverse cosine, our angles must be reported between 0 and pi. Remember, not the degree measures, we want the radians. Okay, so where is sine theta equal to 1 between here and between negative pi over 2 and positive pi over 2? Pi over 2. So pi over 2 is our answer there. Inverse cosine of root 3 over 3, root 3 over 2. We think cosine of what equals root 3 over 2. Cosine's x values, so x values root 3 over 2 at pi over 6. So pi over 6 is our answer for this one. Inverse sine of negative root 2 over 2. We're looking for where the y value is negative root 2 over 2. So at what angle theta is the y value, since it's sine, negative root 2 over 2. And remember, we don't work up here, we work quadrants 1 and 4. Y value negative root 2 over 2, right here at negative pi over 4. Inverse tangent of 0, we're looking for where the tangent, so tangent of what angle theta equals 0. Remember, tangent is y over x, so we're looking for where y over x is 0. Only way that can happen is if the y value is 0. So along our range for inverse tangent, the only place where the y value is 0 is right here. So that would be 0 radians. 0. Inverse tangent of negative 1. Remember, tangent values are negative 1 at either pi over 4 or negative pi over 4. And since it's negative 1, we know it is negative pi over 4. All right, now we're getting into our compound trig functions. So with these, like 6 through 10 here, what we have to do is we work the inside, follow the order of operations, and work the inside problem first. So first we think, all right, inverse sine of 1. So inverse sine of 1, we're looking for an angle where the y value is 1. That'd be pi over 2. So inside the parentheses here, we've got pi over 2. And then we simply evaluate the outside part. Sine of pi over 2. Forget this ever existed. Forget the fact that it was inverse or anything. Sine of pi over 2, we go to pi over 2, report the y value, it happens to be 1. Notice how it seemed like the sine and the inverse sine just canceled out. That doesn't always happen, so it's always a safe bet to work them inside out following the order of operations. All right, same thing here. First we evaluate cosine of pi over 2. Cosine of pi over 2 is 0. X value at pi over 2, so that's 0. Now we do inverse cosine of 0. At what angle is the x value 0? It happens to be pi over 2 again, so they canceled out again. Does not always happen though. Okay, next, sine of 4 pi over 3. So inverse sine of sine 4 pi over 3. So first we take sine of 4 pi over 3. 4 pi over 3 is down here. Sine of that is the y value there, so negative root 3 over 2. So now we do the inverse sine of that. Inverse sine means we want the angle in the first or fourth quadrant between negative pi over 2 and positive pi over 2, where the y value is negative root 3 over 2. That'd be down here at negative pi over 3. So there was one where when we had an inverse on the outside and traditional on the inside, it didn't just cancel out. So negative pi over 3. Next, sine of inverse tangent root 3 over 3. So inverse tangent root 3 over 3. We can derive these. We're essentially looking for which of our angles does the tangent of that angle equal root 3 over 3. So the tangent equals root 3 over 3 at pi over 6. We had a silly way of remembering that. Root 3 over 3 is the tangent value here because 3 plus 3 is 6. At pi over 4, these are the same, so you know the tangent is 1. And at pi over 3, there's only one 3, so that's just root 3. So those are our three tangent values at those three angles, which is why it's a silly way to remember those. All right, so moving along. So inverse tangent of root 3 over 3 is pi over 6. Had it been negative root 3 over 3, it would have been negative pi over 6 down here. So now we just do the sine of pi over 6, which is simply the y value at pi over 6 here, so 1/2. All right, inverse tangent of sine 0. So sine 0 means sine 0 radians. 0 radians is right here. Y value there is 0, so sine of 0 is 0. Now we do inverse tangent of 0. Well, that is similar to one we did earlier. Inverse tangent of 0, we got it again here. So we know the answer is 0. This is the only place where y over x is 0 is when y is 0 and x is 1. So 0 again. All right, transitioning here in 11 through 13, really 11 through 15, we have problems where we take an inverse trig operation of something that doesn't appear on the unit circle. So when that occurs, we take this inverse trig as information to draw a triangle. Just remember, this represents an angle. So even though I don't know the precise angle on the unit circle, whose sine of that angle equals 4/5, I can certainly draw a triangle for which that's true, and then take the cosine of that angle. So I take this as drawing this triangle, first quadrant, since it's positive and it's inverse sine. This angle here is theta. So 4 is opposite because sine is opposite over hypotenuse, right? So 4 opposite, 5 hypotenuse. So now I want to take the cosine of this angle theta. But in order to do that, I got to do adjacent over hypotenuse. So I got to do Pythagorean theorem to find what this adjacent side is. We'll call it, let's call it a for right now. So we've got a squared plus 4 squared equals 5 squared. You might recognize this as a Pythagorean triple. A squared plus 16 equals 25. Subtract 16. A squared equals 9. Square root. And we get a equals 3. So we got this is 3 now. So now I take the cosine of angle theta, and it is adjacent over hypotenuse, or 3/5. That's how we perform compound trig functions or trig operations where the inverse trig operation is of a coordinate that's not on the unit circle. Okay, same thing here. Again, it doesn't really matter what's out here. Our first step is still to draw a triangle from this information. So we know that cosine theta equals negative 5/13. That's the information that we have. So we draw a triangle where cosine theta is negative 5/13. And we draw it in the second quadrant because inverse cosine draws from the first two quadrants. It can only be negative in the second quadrant. So this, remember, our angle theta is always that angle closest to the origin. So this is 5 and this is 13. And remember, the negative has to be one of the legs, can't never be the hypotenuse. So that's how we make it negative 5/13. And now we want to do tangent theta of this theta. But tan theta will be opposite over adjacent. Remember, TOA, opposite over adjacent. So I need to find what this opposite side is, just like I needed to find what this adjacent side was over here. So we perform Pythagorean theorem. Negative 5 squared plus b squared equals 13 squared. Solve this, another Pythagorean triple. 25 plus b squared equals 169. B squared equals 144 if you subtract 25 from both sides. And so square root and you get b equals 12, which is the square root of 144. So we get this is 12. This is in the second quadrant. That's positive. Now we can find out what tangent theta is equal to because we know what opposite is. So tan of theta, and I'm doing tangent because that's what's on the outside here. This just becomes this angle theta. So tan theta equals 12 over negative 5. So negative 12 over 5 is our answer for that second one. All right, I'm going to slide this out of the way so I have a little more room to work over here since I won't need my unit circle anymore. Okay, so finally I've got cosine of inverse tangent negative 2/3. So cosine of this. So I want to find cosine theta, but first I have to draw the angle theta using this triangle. So I know I've got to be in the fourth quadrant because that's where inverse tangents are negative. So fourth quadrant, angle theta next to the origin. Opposite over adjacent is 2/3, so 2 over 3. And remember the negative one is this, is based on the quadrant. So in the fourth quadrant there, our x is positive, but our y is negative. So that's how we get negative 2/3 there. And then we use Pythagorean theorem, since if we do cosine of this, we need adjacent over hypotenuse. We need the hypotenuse. So we find our hypotenuse using Pythagorean theorem. 3 squared plus negative 2 squared equals c squared. 9 plus 4, which is 13, equals c squared. So the square root of 13 equals our hypotenuse. The square root of 13. And now we simply take the cosine theta, which is adjacent over hypotenuse. So we've got 3 over radical 13, but it's not proper to leave an irrational number in the denominator. So we rationalize that denominator by multiplying by root 13 over root 13. So I have 3 root 13 over 13. That's my final answer for that problem. Okay. Now we have more of the same, like 11 through 13, but instead of them both being integers, whether it's 4/5 or negative 5/13, now we have variables. So the nice part about variables is that we can solve these just by drawing a triangle in the first quadrant. So always first quadrant. So I know inverse sine of 1 over x means that sine theta equals 1 over x. And then I want to compute the value of cosine theta. At the end of the day, that's what I want to find, because that's what I want, cosine. So sine theta equals 1 over x. Let's draw first quadrant, 1 over x. So I've got theta next to the origin, 1 opposite, x hypotenuse. Now for cosine theta, I need adjacent over hypotenuse. So I need to figure out what adjacent is in terms of x and 1 here. So I can use Pythagorean theorem to come up with that. I call it a for right now. Call it a squared plus 1 squared is b equals x squared for c. So a squared plus 1 equals x squared. Subtract 1, I get a squared equals x squared minus 1. And then take the square root to get a by itself. So the square root of x squared minus 1 is what a is. So instead of writing a, I can instead rewrite it as the square root of x squared minus 1. And now, since I have all three sides in terms of x, I can figure out what cosine theta is. Simply adjacent over hypotenuse. So it is, I'm just going to write it right here, the square root of x squared minus 1 all over x. And that is the cosine of inverse sine 1 over x. So again, just like anything else, just like any time that's not on the unit circle for an inverse trig function or inverse trig operation, you are always just considering this as instructions on how to label the sides of a triangle, knowing that sine is opposite over hypotenuse, so 1 is opposite, x is hypotenuse. That's exactly what I did here. Solve for the other side, and then evaluated whatever's on the outside of the parentheses. Okay, last one on this page. We have secant of inverse sine x over square root x squared plus 4. So it looks a little scary, but it actually ends up being pretty simple once you get into the nitty-gritty of the calculations. So again, we treat this as instructions to draw a triangle. Always first quadrant if we are working with x's. So first quadrant, So theta is here. Opposite over hypotenuse is x over the square root of x squared plus 4. Okay, I need to do secant, which is the reciprocal of cosine. Cosine being adjacent over hypotenuse, so it'll be hypotenuse over adjacent is what I'm looking for. So I need to find the adjacent. Let's just call it a for right now, as in a squared plus b squared equals c squared. So a squared plus b squared being x squared, and c squared being the square root of x squared plus 4 squared, is c squared, right? So we've got x squared plus 4, because the square root of something squared cancels, just x squared plus 4. We've got a squared plus x squared. Subtract x squared from both sides, and looky looky, cancels out. A squared equals 4, a equals 2 once we square root it to finish it off. So a equals 2. So this is actually 2. So that's not our answer. We want secant of this angle theta. So secant theta equals hypotenuse over adjacent. So the square root of x squared plus 4 all over 2. And that is our final answer. Okay, so last problem on this page, we have naming the bearing of each pathways. Name the bearing of each pathways, and what I should have included on here was a cardinal direction, this being north, east, south, and west. So now I just name each one. So it's O to A. O is this origin point right here. A is right there. So remember, we always name bearings by either starting at north or south, and then go a certain number of degrees, however many degrees, either east or west. So it's north, so many degrees, east or west. So it's always north or south first. I wanted to say north or south. That's what goes first. Then you say so many degrees, and next is east or west, depending on which way you're going. So let's do some of these to refresh ourselves with this. So O to A. So O to A is right here, this line. So for this one, we need to figure out what that angle is. And it's 23 plus 40, which is 63. So O to A is north, 63 degrees west, because it's west of north. So north, 63 degrees west. So that is for O to A. Next, we've got O to B. O to B is just point O to point B right here. This angle right here is 23 degrees as referenced there. So it's simply north 23 degrees west. O to C right there. Now we're a little bit east of north. It's no longer to the left of north, it's right, that's east. So O to C is north 13 degrees east. And again, that's this angle right here being 13, O to C. All right, next, O to D, right there. So I still start, even though I'm close to east, I still have to measure it from north. So I want that angle. That's 13 plus 52, which is 65 degrees. So I'm north 65 degrees east. Okay, O to E, and remember this is east, not point E. Point E is down here. O to E, we are relative to south now because we're closer to south than we are to north. And then we say, okay, south and this many degrees east, because east is this way. We're east of south. 17 plus 31 would be 48. So we are south 48 degrees east. Okay, that's for O to E. O to F. Let's look at O to F. So we need this angle right here because here's F. O to F would be south 17 degrees east. And then O to G, the OG bearing. So we have 34, so we have south 34 degrees east. So here's 34 degrees. This angle measures 34 right there. So south 34 degrees east south 34 degrees west. Since we're now east is this way, to the right of south. We want left of south, which is west. So south 34 degrees west. And the very last one, we have H. Again, we don't measure relative to west. We always measure relative to north or south. We're closer to south than we are to north. We add those two up to find this whole green angle. That's 54 degrees. So we're south 54 degrees west. South 54 degrees west. And that concludes the Page 1 podcast.